Hi there, and welcome to our second video in the Integrated Math 1 video series on arithmetic sequences. Let's go ahead and begin our lesson today with the warm-up for today. Again, try to use mental math as you go. Alright, so hopefully you were able to solve those six. I just wanted to quickly say that I do have some students in the room with me for this session, so I'm going to have them share out from time to time. So if you hear some other voices, they're going to ask questions and those kind of things. I just know that they're in the room for this session as well. So let's go ahead and get started with number one here. 71 minus 36. Number of different ways you can go about doing this. For me, my first strategy was to subtract 30 first, and 71 minus 30 would be 41, and then subtract an additional 6 to get you down to 35. Did y'all have any other strategies there? Did y'all get 35? Okay. All right, number two. Solve x plus 15 equals 21. One way you can do this is just to think about like what number plus 15 equals 21. You don't necessarily have to go through the step-by-step process that you may have done before. And just think that 6 plus 15 equals 21, and just kind of logic through that. Any other strategies that y'all have done on that one? Did y'all subtract 15 on both sides maybe? You could do that as well. But yeah, x equals 6 in this case. Number three, 71 times 4. One way to do that is instead of multiplying by 4, you can multiply by 2 twice. And so one of the ways to do that here is, let's see, 71 times 2 is 142. And then just multiply by 2 again, and you get 284. Did y'all do it differently? How'd you do it?
Multiply by 4 times 70 and 4 times 1.
Good, yeah, 4 times 70 you can do pretty quickly is 280, and then the 4 times the 1 gives you 4 more. Any other strategies? Okay, cool. Number 4. As we've seen in previous videos, we do have a decision here to make. We can either multiply by 33 first, or we can divide by 13 first. And in this case, dividing by 13 is a lot simpler than multiplying by 33. So 26 divided by 13 is 2. And then we can multiply 2 times 33, getting us 66. Any other strategies there? All right, and then number 5 here, we've talked about percents before. One of the things you want to do here is just take the numbers involved. So take 7 and 13 and multiply them together and then adjust the decimal afterwards. So 7 times 13, 7 times 10 is 70, 7 times 3 is 21. Add those together, you get 91. So it's some version of 91. It could be 910. Tack on another 0 here. It could be 91, it could be 9.1, it could be 0.91, it could be 0.091, but it's some version of 9 and 1 together. You just have to make sense of it. 9.1 is still too much. That would actually be 70% of 13. Move the decimal one more place, you get 0.91, which makes a lot more sense there. Any other strategies there? Maybe you multiplied 0.07 times 13 by hand, maybe. Did you get this? Yeah. What did you do? Oh, you did the same thing. Okay, cool. All right, and then lastly, number 6. Just a quick estimate. Let's say that you check out at a store and with these 3 items, and you want to just have in your mind like it should be about blank, right? As you walk towards the cashier. Well, if you take the whole numbers here, so or the integer values, 11 and 3 is 14, and 5 is 19. And then the cents add about to 1 more. So if we were to estimate this pretty quickly, we would say it's about 20, right? Because you got 71, and then a little bit more than 20, 25, somewhere in that range. So altogether, it makes about 20. Any questions on those 6? We'll continue to work on this mental math idea as we continue on. All right, so let's go ahead and get into our lesson today, in which our goal is these 2 things. One is to recognize arithmetic sequences in a real-life situation, and the second one is to analyze patterns to create arithmetic formulas. In our last video, we talked about the corral task, And this video will continue in that same idea with some other real life situations. So, let's get into it. So we've got this calendar. This is our real life situation we're starting out with, is a calendar. And I want you to just think for a moment, what patterns do you see in this calendar? Try to list at least 3 patterns that you see in this calendar. All right, so what are some things that we're seeing here? Noticing patterns about this calendar. Anything? What do you see?
When you go down diagonally to the right, it goes up by 8.
When you go diagonally to the right, so from 7 to like 15, for example, to 23, what did you say happens?
It goes up by 8.
Goes up by 8. Okay, good. Yeah. So diagonally by 8. What else? When you say diagonally, like that direction. Yes?
As you go from day to day, it increases by 1.
Okay, so from day to day is a +1 as you go maybe to the right or wrap around to the next row there. Okay, good. So about from day to day, you add 1.
When you go down in the column, it increases by 7.
Okay, so when you go down in a column, so from like 7 to 14 to 21 or 6 to 13, you're adding 7 as you go down. Okay, what else? Any others? Does anybody look at diagonally this way? What do you add there?
6.
Add 6, yeah. So say plus 6 as you go diagonally this way. All right, any other ones? Okay, so let's take some of these and see if we can come up with a formula or an equation to represent the relationship between the number in the sequence and then the actual value. So let's take diagonally by 8. So let's start with maybe the 7 here is what we'll start with. So if we write out the numbers in this sequence, we have 7, and then the next one's 15, and then the next one's 23. And while this calendar ends, we can still think about like the pattern here and what would happen if it continued on forever. So the next number would be what? 31. Again, that's not necessarily on the calendar here, but we can think about what would happen here. The next one would be 39, and so on. So this is the first term, this is the second term, third, fourth, fifth, and so on. So when I think about, if we know the term number, how can we get the actual value? So if we wanted the 15th term, how can we find out what that number is? So let's see if we can come up with a formula. So take a moment and just see if you can figure out, like, is there some way you can like think about how to produce either more numbers in this sequence or how to jump to like a particular value? So see if you can come up with like some formula for this. We'll just brainstorm real quick for a few minutes. Okay, were y'all able to come up with anything? Any ideas? Maybe just like, what do I do to get to the next one? Every time, what am I doing each time? Adding 8, right? So we can think about it, that's what we call recursively, is like just from one term to the next, what are we doing each time? That's what we call a recursive formula. So we're adding 8. So just to introduce you to some symbols here, we would say a sub n equals, so this is just like the outcome here, a sub n equals a sub n minus 1 plus 8. So this is the previous term. So we're adding 8 every time to the previous term to get the next one. So for instance, we would say the second term is equal to the first term plus 8. The third term is equal to the second term plus 8. The fourth term is equal to the third term plus 8. It's that recursive idea. So if I were to ask you what the sixth term is, what would you do? You'd add 8 to what? Yeah, the fifth term, right? So that's all we're saying here is you're adding 8 to the previous term, and this is how we kind of write that in mathematical notation. The nth term, so any term, the nth term is equal to the term before it plus 8. But this is only helpful if we're going to the next term, or maybe like within 5 or 6 terms. I mean, if I were to say what's the 90th term here, that would take forever to do it that way, wouldn't it? Because you'd have to add 8 over and over and over and over and over and over again. Whereas there is a quicker way, right, to do that. So recursive is really good in defining things when you're just trying to get the next term or the term after that. But when you're trying to jump to a term way far away, then this is maybe not as good. Okay, so let's go back to think about it maybe a different way. So this term here, you can think of as being 7, right? The next term is 7 plus what? 8, right? One time, right? The next one would be 7 plus 8 times 2. Right, remember at the crowd task we had like the constant value, but then we added groups of 3 or 4. Here we're adding, we're starting with 7, we're adding groups of 8 each time. And so we're going to continue this and say the next one would be 7 plus how many multiples of 8? 3. Now let's just check here, right? 8 times 3 is 24 plus 7 gives us the 31. So that works out, right? And then the next one would be 7 plus 8 times 4. So let's see if we can generalize this and say that a sub n is equal to, well, what's consistent throughout? Like what doesn't change about our expression throughout here? The 7, right? 7 plus, yeah, I heard somebody say that 8 doesn't change either. What does change? Yeah, whatever you're multiplying 8 by. Okay, so in parentheses here, whatever that number is, it changes, right? So that's going to be based on the term number at the top. Well, let's see. How does it relate to that term number? So when it was 2, we put a 1 in here. When it was 3, it was 2 in here. When it was 4, we put 3. When it was 5, we put 4. How do those relate? Subtracting 1. It's 1 less, right? So it's not the term number in the parentheses. It's the term number minus 1 that goes in there. Does that make sense? So we're going to put, if our term number is n, we're going to put n minus 1 in here. And that can be our expression. So let's try it. We said that the sixth term was going to be, what, 47? Is that right? Okay, let's check it. So if we put 6 in here, we should get out 47. Let's check it. 6 minus 1 is 5, times 8 is 40, plus 7 is 47. So we can use this formula to get to any term we want, like that, right? So if we wanted the 101st term, 101 minus 1 is 100. This is how it works out nicely, right? 100 times 8 is 800, 807, right? Would be the 101st term in this sequence. And you probably haven't seen something written in this form before, but this is one of the versions of what we call an arithmetic sequence. So if we were to generalize this, we would say a sub n equals, what did 7 represent? Yeah, the first term in this sequence, right? So we're going to call that a sub 1. That's the first term. That's how we denote the first term. Plus, wasn't 8 just like how much we're adding each time? So we're adding 8 each time, so we're going to call that the common difference, which is D, and then it will always be term minus 1. If we start with the first term, it will always be a term minus 1. So this is maybe like a general, like if you were to look at a textbook and see the formula for an arithmetic sequence, this is what you would see. But just know that like we can rewrite this too. So if we were to rewrite this, we'll do that in red here. Come down here, rewrite this. We could distribute the 8, couldn't we? Do you remember distribution? We could multiply 8 times n and 8 times negative 1. So we're going to get 7 plus 8 times n is 8n, and then 8 times negative 1 is negative 8. So we can simplify the 7 with the negative 8 and get negative 1. So another version of this would be 8n minus 1. So let's go back to, what was it, the 6th term we were testing earlier? Let's try it again. 6 times 8 is 48, minus 1 is 47. So we still get the same value each time. It's just a different version of it. These are what we call equivalent forms. Okay? But this is what you'll see with arithmetic sequences more often than not. And then this is what you'll see later on this year when we get into what we call linear functions. You'll see it more in this version where we have like slope and y-intercept. So we'll get to that maybe later this year. Okay, so what I want you to do is I want you to try this same process to come up with an expression for one of these other ones. So let's do this one here. Adding 7 when we go down as a column. See if you can pick one of the columns to start with and come up with a formula for that column. And again, you can assume that column continues on forever, even though it doesn't in this calendar. So see if you can do that. Okay, let's go ahead and take a look at this vertical pattern, adding 7 each time. And you can probably already see that this plus 7 is going to end up being our common difference, the number that's adding each time. So if we look at Saturday, for example, and you could have done a different column, but if we look at Saturday, it's 3, 10, 17, 24, and if this pattern were to continue, the next one would be 31, right? And so on and so forth. So let's see if we come up with a formula for this. How did y'all go about doing it? Anybody want to share? The same way? So how did you write like the various like numbers in a different form? So you wrote 3 as just 3. And then 10, how did you write that? 3 plus 7 times 1 essentially, yeah. And then the next one would be 3 times 7, or 3 plus 7 times 2. Yeah, because that'd be 14 plus 3, right, which is 17. So we're starting with 3, and we've added 7 twice, as the times 2 comes in, right? The 24 is 3 plus 7 3 times. That's the definition of multiplication, right? Is groups of 7. So we've got here for 24, we've got 3 plus 7 times 3, and so on. So were you able to come up with a formula for this? Okay, so a sub n equals, did you do recursive or explicit? Explicit's the one where we can jump to any term at any time that we did there at the end. You did explicit? Did everybody do explicit? That's probably the one that we finished on. So that was the one where it was like 3 plus, what's the common difference? 7 times n minus 1. Yeah. So yeah, that's the form that all of these take, right? It's 3 plus 7 times the 1 less than the term number is how we can get all of those terms. And so we can jump to whatever term you want by doing that. Now just to go back, so this is explicit. And then this is recursive. So explicit, we can put in the term number here, and it outputs the value of that term. Recursive says just how do we get from the one term to the next. So if we're trying to get to the nth term, we can take the n minus 1 term, which is the one before it, and add 7. So that's the difference between those two. So the advantages to these, if I'm trying to get to the 6th term, I don't really want to create this formula and then substitute in 6 just to get to the next term, right? I would probably just do this thought. I wouldn't even write this out, right? I would just think like, oh, I'm adding 7, so to get to the next term, I'll just add 7. But this is how we would write it in math notation. Now, if I was trying to get to the 75th term, I would try to come up with a formula and then put in 75 for n. And we could do this for the plus 1, we could do it for the plus 6, we could do it for any of these patterns that we're seeing, right? And so this is the idea of these two. So recursive and explicit, those two forms. Again, for explicit, the formula is a sub n equals a1 plus the common difference times n minus 1. So again, the first term in our sequence, whatever you're adding each time, and then n minus 1 will always be there as long as you're starting with the first term here. Whereas recursive is more of that repetitive process to getting one term to the next. So we're going an equals a1 plus whatever that common difference is. So we're adding d each time we go in this process. All right, so let's see if we can apply this to a different scenario. So let's take one of these patterns that we're seeing, and let's just see if we can maybe apply it to this new table. So pick a pattern, and then see if you can come up with a formula to represent that pattern. All right? See what you can do. All right, so let's see what different strategies we came up with, what patterns we saw, those kinds of things. So does anybody want to share maybe a pattern that you saw up here? Yes?
I did diagonal left starting at the 11.
Diagonal left starting with the 11, and what did you notice happened each time?
It increases by 10.
Increases by 10. Okay, so if you were to continue this table out, you could think about what that sequence would look like. You want to share what your formula was that you came up with?
A to the n equals 11 plus 10 times n minus 1.
You don't understand what she did there? You're good with that? So yeah, this is the first term plus the common difference, so it's plus 11 or plus 10 each time times n minus 1. So we could even think about what the millionth term in this sequence would be, right? It wouldn't be too bad, might need a calculator, but we could do that, right? Pretty quickly. All right, do anybody see a different pattern that you came up with? Yes.
For the columns, you go down, it goes up by 12.
Okay, which column did you specifically look at?
The first one.
Okay, the first column here goes up by 12 each time. So what was your formula?
A sub n equals 1 plus 12 times n minus 1.
Okay, good. And again, these are just one version of this formula. We could rewrite it if we wanted to, and we'll just do this one for example. So if we rewrote this, it would be 1 plus 12n minus 12. So an equivalent version would be a sub n equals, let's see, 12n minus 11. Should work as well. So this is an equivalent form. So just know that there's actually an infinite number of ways to write this. Just kind of give you a quick overview. You could actually start with any term you wanted to. We've been starting with the first term, right? And using that as our starting value. But you could start with the third term, the fifth term, the seventh term, whatever you wanted to. So as long as whatever term number you put here, you're subtracting that value here. So if you start with the seventh term in your sequence, just subtract 7 from it instead. It's not like it's a little more complicated. But let's just for example, let's do his sequence here, but with the fourth term. So a sub n equals, what's the fourth term? 37 plus 12 times what? Yeah, n minus 4 instead of 1. Because we took the fourth term instead of the first term. Let's just check and see if this works. Are these equivalent? 37 plus 12 times n minus 12 times 4 is 48. And you get 12n minus 11. So it is equivalent to that one, which of course is equivalent to the first one. So if you don't get that part, or we can use any term, that's okay. If you're okay with just using the first term, that's fine. But I just wanted to show you that we could use any term we wanted to. Does anybody else have a different pattern that you looked at that you want to share? There's lots of other ones. Did you notice the overall pattern of the table? What were they?
2.
It's adding 2 each time, right? It's the odd numbers is really what it is. So, all right, cool. Let's go on to our last example, and then we'll be done for this session. So we've got an auditorium here, and the question is, how many chairs are in each row? And if we extend this out, is there a way to calculate how many chairs we would need for any row? And so let's start out by trying to write a function to represent the number of chairs. And then once we've done that, let's see if we can use that to find out, like, if there's 101 rows, how many chairs would be in that last row, that 101st row? So take a minute, see if you come up with a formula, and by the way, I think there's, let's see, let's count them together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in the first row. And then 14 here, 17 there. So 11, 14, 17. See what you can do. All right, so let's talk about a formula for this. We were able to come up with one. Over share. A sub n equals, go ahead.
11 plus 3 times n minus 1.
All right, cool. So let's check it. So we got first term plus the common difference, which is 3, because we're adding 3 each time, times n minus 1. Now we haven't seen a situation like this, but I want to make sure that you understand that if we were to start with the last one being our first term and it getting smaller each time, the common difference would be what?
Minus 3.
Minus 3. So there'd actually be a minus 3 here, right? Now we're not doing that, but I just want to make sure you understand. Like if it's getting smaller each time, you're just going to have a subtraction here instead of a plus, because it's going to be a common difference that's negative there. So yes, did anybody come up with a different version of this, or did you all use the same one? Same one? Okay. All right, so now if we wanted to find the 101st row, what would we do? Yeah, substitute in for n, right? 101. Okay, so 101 minus 1 is 100 times 3 is 300 plus 11 is, yeah, 311. So I would write that A 101, so the 101st term is 311. Now obviously there are other ways we could write this, but that is one acceptable way. All right. So any questions on arithmetic sequences and how to create a formula for it given the sequence? Anything that you're wondering or maybe have questions about? The big idea here is that we're talking about repeated addition, right? We're repeatedly adding 3 in this case. So keep that in mind, because we're going to see maybe something a little bit different in the next couple lessons. Okay, so we'll wrap it up with our goals for today. Again, hopefully we're able to recognize arithmetic sequences in a real life situation. We're finding those patterns in the calendar, and then analyze patterns to create arithmetic formulas. Given a sequence of numbers, can we create a formula for that? All right. So that's it for this video. I hope you'll join us next time for lesson 3 in this video series.